My name is Anthony Nathaniel, and today in our geography class and in Global Education Zone channel, I'll be talking to you on an important topic in geography known as the Earth's movements and the solar system. So join me as we journey through this interesting voyage. So basically, the Earth movement is basically dealing with the fact that the Earth is moving in space, and the space also contains what we call planets. So today we are going to be talking about the planets and the sun. We're talking about the moon and the satellites. We're talking about proof of Earth's sphericity. We're talking about rotational revolution. We're talking about equinoxes and solstices. Then we're talking about eclipse, dawn, and twilight. So let's move on. Now the planets and the sun. Now we have a universe. Our universe is extremely large, but in that universe we have galaxies, and in those galaxies we have solar systems, or rather we have groups of stars known as nebulas. Now in our own galaxy we have our own solar system, and our solar system is located near one edge, near the edge of the galaxy, and the name of our galaxy is called the Milky Way galaxy. So in this Milky Way galaxy we have a solar system, and in that solar system it contains a special star known as the sun. Now there are different stars, and those stars are different based on their age. But in our galaxy we have the sun, and in the sun there are many planets that surround the sun. And if you've probably heard of this mnemonic: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. Then you also have Pluto. But Pluto was removed from the planets in 2006 by scientists because it did not meet the requirements for the properties of planets. So we have, instead of 9 planets, we now have 8 planets and the sun in our solar system. And it's important to know that our solar system is full of stars, full of asteroids, full of meteoroids, full of different objects. But these planets and the sun are the major components we'll be talking today in our geography class. Now those planets are just listed together. They rotate around the sun. They revolve around the sun. So, and those planets, let's start from Mercury. Mercury revolves around the sun and is the closest planet to the sun. And Mercury, it takes 88 days for Mercury to revolve around the sun. And when you say revolve around the sun, it's just like when this is sun, you are moving around the sun. So if you move around the sun once, that's 1 revolution. If you move twice, 2 revolution, 3 revolution. So for Mercury to revolve around the sun once takes 88 days for Mercury to do that. And Mercury does not have any stars. So we're also talking about those. Mercury does not have any moon. We're talking about moon later. Then we have Venus. After Mercury, in closest to the sun, we have Venus. And Venus is the second closest star. Second closest planet to the sun. And Venus, it takes Venus 225 days to revolve around the Earth. That's to go around the Earth one complete time. So, and then we have the Earth. Our Earth is the 3rd planet in proximity to the sun, and it takes our Earth 365 1/4 fraction of days to revolve around the sun. That's 365 and a quarter day for our Earth to revolve or rotate around the sun. But that quarter day is usually combined together into 4 to make 1 day, which is added at every 4 years to form a leap year. So that is why we have 365 days in a normal year and 366 days in a leap year. So then after our Earth we have Mars, and Mars, it takes Mars 687 days to revolve around the sun. After Mars we have Jupiter. It takes Jupiter 11.9 years to revolve around the sun. After Jupiter we have Saturn. It takes Saturn 29.5 years to revolve around the sun. After Saturn we have Neptune. It takes takes Jupiter 11.9 years to revolve around the sun. It takes Saturn 29.5 years. It takes Uranus 84 years. Then it takes Neptune 164.8 years to revolve around the sun. So you can see that as the planets get far away from the sun, it takes more time for them to revolve around the sun. Starting from Mercury, which is just 88 days to revolve around the sun, down to Neptune, which is 164.8 years. So that is, we talked about the planets and the sun. So all these planets, they revolve around the sun periodically, and their rate of revolution around the sun, they also have their distances from the sun. and the more they are distance from the sun, the more the time taken from them to revolve around the sun. Actually, there's a law for that known as Kepler's law, but we are in geography class, so I won't delve into that. So let's continue. We have the moons and the satellites. Now let's talk about the moons. Each of these planets, they have their own moons, and when we talk about a moon is basically a body. A moon is also known as a satellite. Now a satellite, if you get attracted to somebody else and then you begin to follow the person about, that is like you are like a satellite to that person. For example, also if you have a school and you have another school beside that school, now that school is close to the first school. Now, and if that school, that second school is smaller than the first school, it's called a satellite campus, right? So we have main campus, satellite campus, main city, satellite city. So that satellite is like a supporter, is like an admirer. So, and even every planet in our solar system, they have their satellites, but not every. Actually, most of them have their satellites, but not every. Some of them have asteroids rotating around them. Some have meteoroids. So those asteroids, they are like fragments of pieces. So if you are interested in knowing more about the solar system, you can check the description of this video and hit me up on WhatsApp too, so I will continue the discussion. But for now, for today, we are just talking about it in plain terms, in terms of geography. So now let me continue my talk on the Earth's movements and the solar system. Now, those satellites, they revolve around the planets. These planets I've talked about now: Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune. So Pluto is not involved. Don't count Pluto among the planets again. It has been removed by scientists in 2006. So let's move on. Now, those planets, most of them have their satellites. Now, for example, the Earth has one satellite. That's the I'm going to list the ones that have satellite. The Earth has one satellite. Then Mars has two satellites, and those satellites, they are also known as moons. So if somebody tells you the Earth has one moon, it's also correct. But the Earth satellite is specifically known as the moon, and we know the moon, which is 384,629 384,629 what's it called again? Kilometers. Yes, 384,629 kilometers away from the Earth. So the moon that's the distance from the Earth and the moon. So that aside, the Mars has two satellites. Then Venus, Earth, Mars, Jupiter has 12 satellites. Jupiter has the most satellites in our planet around the solar system. Then we have Saturn has 9 satellites. Then we have Uranus has 5 satellites. Yes, 5 satellites. Then Neptune has 2 satellites, and so on and so forth. So, and even now, what I'm describing is the limit of our understanding, because what we've been able to do now, we've only been able to understand the Earth's surrounding, but our universe is so large. Even our Milky Way, our solar system itself is larger than we can imagine. So if we explore more, we are going to discover more. But these are the ones in the limits of our scientific knowledge and research. These are the ones we've been able to discover. Now let's move on. The proof of the Earth's sphericity. Now, when you talk about sphericity, you are trying to talk about the fact that something is round, right? Now, the Earth's sphericity. When I was in my geography class in SS1, I remember my teacher. His name was Mr. Pupola, and then he used to teach us about the Earth's sphericity. And because of that, I remember him to this day, because the way he eagerly taught us then made me remember the several proofs of the Earth's sphericity. Now, let me list them out for you. The first one is the circumnavigation of the Earth. So between the years 1519 and 1522, the Earth was circumnavigated. And when you talk about circumnavigating, you are talking about the fact that the Earth, when you circumnavigate something, you are moving around that thing. So there was a man named Ferdinand Magellan in the 16th century, in the early 16th century. So between the years 1519 and 1522, he and his men, they set around the Earth to discover whether the Earth was truly flat or it was spherical. Because then in those days, people thought that the Earth was flat like a table, that when you go to the edge of the Earth, you are going to fall down. But then Ferdinand Magellan, Magellan in the 16th century, he decided that, okay, no, I'm not going to go on believing this thing. So he decided to prove by himself. So and when he was able to go around the Earth and come back to his starting point, people now believe that the Earth is actually spherical. And even today, if you try it, if you take a plane, provided your plane has enough fuel to go around the Earth, and you go around the Earth one time, you get back to your starting position. So the Earth is spherical because of that. Then we also have the circular horizon. When you go up, when you look around, you see that everywhere is a circle. When you go to a high tower, maybe you are standing on a tower, and then you look around, you see that everywhere is in a circle. So there is no, if the Earth was spherical, you'll be seeing the edges of the Earth as a rectangle, right? But if you're in, if like those of you that that live in upstairs, like story buildings or skyscrapers, or you've ever gone that high, you've gone that high and you manage to be at the balcony, or maybe you manage to be close to the top of the building, you can be able to observe that around you is a circle. So that shows that the Earth is actually spherical. Then we also have ship's visibility. When you are if you've been able to go near a river, when you see a ship coming, you see that the ship is not totally visible at first, but when it gets closer, the whole of the ship becomes visible. And even not only ships, when you look at things like when you look at things coming from afar, like even let's say people, and when a person is coming from a far place, you might not see the person's whole body, but when it gets closer to you, you see the person's whole body. That's because the Earth is curved, so you cannot see the whole of something when that thing is below your horizon or your horizon. So that is another proof. Then we also have apart from ship visibility, we also have different other proofs. We have area photographs taken by people, and even in the year 1969, Neil Armstrong and his men, and they went on an Apollo mission in the 20th century to prove the fact that Earth is spherical. So they landed on the moon. You will have heard of that Neil Armstrong is the second man to land on the moon after Yuri Gagarin from Russia. So now when he landed on the moon, they were able to show that the Earth, when you view the Earth from the moon, you see that the Earth is actually spherical. So that's a proof. And even most of the photographs from the Earth taken in the 20th century are still the photograph you see in your textbooks, in your geography textbooks. You still see those photographs. So that shows that the Earth is actually spherical. So apart from area photograph, we also have lunar eclipse. So whenever the Earth comes between the sun and the moon, so that's what's called an eclipse. So whenever the Earth comes between the sun and the moon, the shadow of the Earth cast on the moon is always round in color. Because if this light is shining now and I put a round object before it, then the shadow of that object will be cast on this board, and then that shadow will be round. So your shadow is a reflection of the shape. And if the Earth's shadow is round, that means the Earth is also round. So that's also another proof. If you are asking your examination or anywhere you ask your WAEC, NECO, when any exam you ask, these proofs are standard proofs and they work always. Then we also have other proofs like driving of poles of different lengths, of equal length on the ground. You see that one of the middle pole, when you drive 3 poles on the ground, the middle pole is a little bit slightly projected than the others. We also have different other proofs of the Earth's sphericity, the circular origin, circumnavigation of the Earth, and so on and so forth. So there are more, and you can even check those in your textbook. So let's move on. The proof of the Earth's sphericity, I've done that. Then we have a rotation and revolution of the Earth. Now the rotation and revolution of the Earth, these are basically the fact that now the Earth, when you talk about something is rotating, I talked about the fact that the Earth revolves around the sun, but as the Earth is revolving around the sun, it's also rotating around itself. Like when it's like something is spinning on its own. Just like when I'm spinning this marker, or if I myself am spinning, it's called a rotation. But if I'm going around somebody else, it's called a revolution. So you understand? So now the Earth is also rotating, and when the Earth is rotating, it's inclined at an angle of 22.5 degree, 2.5 degree on its axis. You understand? So that means the Earth is not rotating perfectly vertical; it's rotating slanted at an angle. So, and because of that, we have some kind of phenomenon which I will describe later, equinoxes and sources. But let's move on. Now, when the Earth rotates, there are different things we can see because of the rotation of the Earth, and those are called effects of rotation. We have day and night. So because the Earth is rotating and the sun is static, now as the sun is shining on the Earth, now this is Earth. Now the sun's ray they are called waves, and those waves, they will hit an obstacle. But when the Earth is rotating, the part of the Earth that is facing the sun is the one that those waves will hit. But the one that is not facing it will not be hit by the wave. So that's why we have night and day. We have day and night, because the reason why we are in day now, the reason why you can see me making this video is because we are in day, and because I can see the sun can reflect its wave on me. But when we are in night, that means the part of the Earth that I am is turned away from the sun. That means I'm not seeing the sun. We are in darkness. But when the Earth rotates back into the face, because the Earth is rotating constantly, when the Earth is rotating back into the plane of the sun, you will see that it becomes daylight again. So day and night is an effect of rotation of the Earth. We also have deflection of oceans and wind currents. So we have the Earth is divided. If this is the Earth, we have what we call the North Pole. Now the inside of the North Pole is at the north and the South Pole is at the south. But instead they are inclined at an angle. So the North Pole is actually inclined at an angle of 22.5 degrees. So because of the fact that the Earth is, when the Earth rotates, it's inclined. So instead of like this, it's actually inclined, it's bent a little bit. That's the natural inclination of the Earth to its own axis. Now, even and when the Earth is revolving around the Sun, it's actually inclined at an angle of 66.5 degrees. That is the inclination to its elliptical. That is inclination to its elliptical path. So elliptical path means the Earth is revolving around the Sun, and the distance from the Earth to the Sun is changing. Because when the Earth is rotating around, is revolving around the Sun, at times to be far from the Sun, that is called I think an apogee. Then when it is closer to the Sun, it's called a perigee. So when it is closer to the Sun, it's perigee, and when it's far, it's apogee. So because of the fact that the Sun, so if we could go deeper and deeper and deeper into this topic, but I want to keep it at the surface level. So let me just not talk about those forces. So but let me just give you a little bit of snippet of what I'm talking about. The snippet is that now those forces involve gravitation, and that's gravitation forces, they vary based on the effects. So and then we have centripetal forces. So I don't know if you are a science student or if you don't feel it, but you know that there's a force that is pushing an object around another thing. So because of many complex forces and even many more that even scientists might not have been able to discover, that is why the Earth sometimes it is far from the Sun and sometimes it's closer to the Sun. That's why sometimes some seasons are always hotter than others, some seasons are closer than others. So scientists are still trying to study and observe this phenomenon. But let's continue our talk. So rotation of the Earth, the effects of rotation of the Earth are day and night. It's because it makes us have day and night. It makes us have deflection of winds and ocean current. So when the Earth is rotating, just like when I'm turning around now, when I turn something around this and maybe there's water on this marker and I'm turning the marker around, some of the water will be sprayed off, right? Now that spraying is called deflection. So because of that, because the Earth is rotating with at some speed, so some of the waters and winds, those are called fluids. Water and winds are called fluids. Fluids. So those fluids, they become deflected. In the northern hemisphere, that is in the top half of the Earth, they are deflected to the right. Then in the bottom half, they are deflected to the left. So and that bottom half is also known as the southern hemisphere. So I don't know if you are able to grasp all this thing I'm saying, but you can, if possible, you might slow down this video to be able to grasp it. But I want to cover as much as possible so that you can be able to kind of catch up as fast as possible, because that's my nature. So basically, well, I've talked about rotation. Then other effects of rotation of the Earth are apparent sunrise and sunset, because the Earth apparently rises and sunsets. So we have time difference from place to place, daily rising and falling of tide. So that's why when you are in a beach, you see that the tide goes back and goes forward. That is the wave. And then in the daytime, the tide is low. Then in the night the tide is high. So and it can occur vice versa, depending on the place, on the part of the Earth you are. So if you are very keen in geography, you are apt in geography, and then you understand it a lot, or you wish to understand, then you should have a very, very keen mind on what I'm saying. But let's continue. Then we also have dawn and twilight. So I'll talk about dawn and twilight at the ending of this video. So revolution is but don't forget that rotation is the movement of the Earth around its axis. Then revolution is the movement of the Earth around the Sun. So then we have equinoxes and sources. So before I was talking about the fact that the Earth is inclined at an angle of 22.5 degrees on its axis, right? Now because of that, we have some phenomena known as equinoxes and sources. Now the sun is away from the Earth. Now if this is the Earth and then we have the Sun here. Now this Sun is casting its ray on the Earth. Now at some times, and at the center of the Earth, which is called the equator, at this equator, then there's a phenomenon whereby the Earth is directly facing the Sun, and then we say the Sun is directly overhead. So and because of that, there are different parts that can be facing the Sun. So as the Earth is rotating around the Sun, some part of it will be facing the Sun at some time, then some part of it will not be facing the Sun. So but here in West Africa, where I am, I'm in Nigeria, West Africa. So and in Nigeria, most of the time we have the Sun overhead because we are close to the equator. But if you are in another part of the world, close to the poles, and when I say the poles, I talk about the edge of the world, like those edges, the North Pole and the South Pole. When you are far away from the equator, or maybe you are in Europe, you are in America, or you are in other non-polar, non-equatorial countries, so you will understand that the Sun is mostly not usually overhead, and that is why those regions are colder, because of that there's little sun And because when you have something directly falling on somebody, you know that that thing will have more effect. But when when that thing is falling from the side, it will, the gravitational effect will not let it have that enough force. But when something falls directly, you know it will have more effect than when it falls obliquely. So because the sun's ray is falling directly in the equator, that's why we have a phenomenon known as equinox. So equinox is when the sun is directly overhead at the equator. Then we also have solstices. Solstices is when the sun is directly overhead at the tropics. And when we talk about tropics, tropics are regions of the earth that are between the equator and 66.5 degrees of latitude. So in a previous video, I've talked about latitude. You can check it out in this channel. I've talked about latitude and longitude. I've explained it in detail. So you can check that if you still want understanding of this. So 66.5 degrees north and then 66.5 degrees south. So and note, the only regions of the earth where the sun can ever be overhead is between the tropics, and that tropic, the northern tropic is called the Tropic of Cancer, then the southern tropic is called the Tropic of Capricorn. So in order not to waste too much time, let's move on to the next part. Eclipse. So an eclipse is basically a phenomenon whereby an object casts its shadow on another object. So instead of the sun's rays to be coming to the earth, for example, if the moon stands between the earth and the sun, the shadow of the moon will be cast on the earth, and that's called solar eclipse. Then if the earth is between the sun and the moon, then the shadow of the earth is cast on the moon, and that is called lunar eclipse. That's all about eclipse. So you should have known about that by now if you are in secondary school. Now we have dawn and twilight, and dawn and twilight is partly as a result of what I've talked about now. It's partly as a result of equinoxes and solstices and the sun being overhead. Now, if the sun is not directly overhead, like in this part of the earth now, when the sun is going, when the sun's rays arrive at the earth, they hit directly at the equator most of the time. But outside the equator, the tropics, some of those sun's rays are oblique, so they are not from the top. They are at an angle, and because of that, they have less power, and because of that too, most of the sun's rays are oblique, right? So that is why we have the phenomenon of dawn and twilight. So dawn and twilight is a result of the fact that at the sun, you can see the sun at the edge. So you know that the sun, if you look at the sky, sometimes the sun is at the top, sometimes the sun is going down. Now in those areas where we have twilight and dawn most of the time, that twilight is a result of the fact that the sun is at the horizon, is close to the horizon for a long period of time before it goes down. So and because of that, most of those part of the earth, the sun never goes directly over it, so it's mostly at the horizon, and that horizon at the edges. So and then when the sun is at the edge before it goes down, it's called the twilight. Then when the sun is at the edge before it rises, it's called the dawn. Now, regions of the equator, like where I am now, Nigeria in Africa, regions of Nigeria and Africa, we will have less of that dawn and twilight. Because why? Because the sun is usually overhead. But in areas where the sun is usually at the horizon, we have that dawn and twilight because the sun is not overhead. So I hope you've been able to gain one or two things from this this kind of a little bit of complicated class, but it's still rightly so. Thank you for watching.